All right, we're going to start with this guy. It's a polynomial, and if you remember back, there are certain things we said. The highest exponent is how many zeros it has. 3 zeros. Then we subtracted 1, and we said two turning points. Then we subtracted 1 and said 1 inflection point. Okay, so it starts at the 3 zeros, 2 turns, 1 inflection. Right now, you graph this, and you notice you exactly can't see the bottom of this. You can't see where it turns on the bottom. So how will you adjust your window? Y, min. So change your Y min until you can see it. I used negative 25, and it came out okay. Yes. 1 inflection point. My board's a little bit off here. Okay. Also, this is an odd exponent, so, and it's positive, so the end behavior says down on the left, up on the right. Remember doing that? Odd and positive. So end behaviors go down left, up right. Okay. Now, do I see 3 zeros? We could also have imaginaries. Yep. I see 1, 2, 3. 2 turns, 1, 2, and 1 inflection point. Inflection point is, it has to do with your concavity. Your concavity says you're caving down, but this guy says you're caving up, so halfway through is your inflection point. Ah, now we're going to label these. A, B. What is A? Relative max. It is relative to this area. What is B? Relative min. Okay, let's label C. C is my inflection point. I just want to put some labels out here. Let's label my zeros. D, E, F. Those are my zeros, or my x-intercepts. Okay? Now, first step through. Let's take a look at domain and range. Are there any exceptions in this graph at all, in this function at all, that any x that I cannot use? No. So my domain are real numbers. Any exceptions in my range? No? All real numbers. Okay? So, God bless you. Maximums and minimums, we know we have relative ones. No absolutes. So how do you find those on your calculator? How would I find point A? Point A, my relative max. Moving thing. Good. Yeah, do that moving thing. So I'm going to pull up my calculator in case you forget it, and I'm going to go. Let me change my window. You're going to go second calc. And I'm going to find my max. So we're going to move the little bug guy to the left, left bound. We're going to move the little bug guy to the right, right bound. And we're going to guess. And we take 3 decimal points. 3 decimal places. 3 decimal places. Rule of thumb, 3 decimal places. So there's your max. Your min, you're going to do the same thing. Second, trace, min. You're going to get your bug to the left of this turning point down here. Anywhere to the left. Get your bug anywhere to the right of it. And yes, there's your relative min. You need these to do your increasing, decreasing, to find your inflection points. So we're going to put this on your graph. Up at A, here's my relative max. Here's my relative min. Okay, everybody get that? Did you get to the left and to the right of your curve? Did you hit the guess yet? Minimum, but see, where you are, you're not at your minimum. Your minimum should be down here. So you didn't push them all the way down. It's left bound. Now bring them all the way to the right. You gotta see that bug past that little right. And yes. Okay? Alright, so we got these two taken care of. Now, increasing, decreasing. It's like your roller coaster. You're looking at your Y values as they go up and down, like a roller coaster, but you're naming this by your X interval. So here I am increasing, going up, 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 until I hit this X value. So I am increasing from negative infinity to this X value. And where else am I increasing? From what point? From point B, from 3819 to infinity. I'm looking at my Y values because that's the value of my equation, but I'm saying to you where my X is going. Remember, increasing, decreasing, you have to give me the X's. Therefore, the decreasing says, okay, I'm decreasing from A to B. I am decreasing from negative 0.523 to 3.189. Now, once you hit all your decreasing and increasing, you should be able to look at it and have one continuous curve. So from negative infinity to the negative 0.5, from the negative 0.5 to the 3.1, I'm just giving you the first decimal, from the 3.1 to infinity. Do I cover my whole curve? Yes. Now, your inflection point. When we talk concavity, we say concave down. Here's my concave down. Concave up. Here's my concave up. Somewhere halfway between this decided, instead of concaving down, they said, whoops, I got a concave up. This guy, this halfway mark, is your inflection point. So to find it halfway, we take the average of your x's. So my inflection point says negative 5.23 plus 3.189 divided by 2. This gives me my x. I like finding the midpoint in geometry. Take the average of your x's. To find your y, we're going to go back to your graph. So don't forget, if you put it in your calculator all at once, you need parentheses. So this x value will give you 1.333. Now, that's your x. To get your y, come back to your graph and go second calc value and put in 1.333. Find that y value. That's the y value that corresponds to that. Okay? So therefore, our inflection point says your y was negative 11.404. a point has to have an x and a y. So if I want the inflection point, I need both the x and the y. My concavity, I name just like I named my x values for the increasing, decreasing. So my concavity for going up is the guy that turns up here. It started here at that x value at the 1.333 and it went up to infinity. The concave down came from the other side, from negative infinity, and stopped when it hit that x value. Okay, that I should also see continuous if I look at both. That's it.
I have a question.
This is one of your big ones.
It's only one of these.
One of the six that you have to pick from. You have to pick 3 out of 6 on part 2. This is one of the 6.
So you don't have to do this. So part 2, 3
You don't have to.
I'd rather do one.
But isn't this a nice one?
Can you do like say all 6 of them, but 3 are wrong?
No, you have to choose. Yeah, you have to choose. Okay, but you would do them all and then cross out the ones that you didn't feel confident with or you didn't finish. Okay, all we have left are your x and y intercepts. Now, notice your x-intercepts are the same as your zeros, aren't they? They're your zeros. The roots, aren't these the roots of your equation here, of your function? They're the roots of your function. That's where it crossed the x-axis. So, if it's okay, I'm going to erase this piece to give me more room, okay? So otherwise I run out of room. So let's do your x-intercept algebraically. So x-intercept, set your y to 0. So we're going to factor. What does each term share? X. Good. So let's factor out an x. I have a trinomial. So therefore I can factor this to 2 binomials. I need to get a negative when I multiply, so I got a plus and a minus. And factors of 5, there's only one, 5 and 1. And I need the negative to be the higher number. I set all of these equal to 0. So x is equal to 0, x is equal to negative 1, x is equal to 5. Here's my intercepts. And that makes sense. Can I confirm those on my calculator? Graphically, can you look at it into your table and see where your zeros are when your y's are zeros, right? That one falls nicely. Your y-intercept says, let x equal 0. So if I plug 0 into the first term, I get 0. Minus the 0, minus the 0, up. Then I get, y is equal to 0. And yep, I should be able to have that same point. So there's all your pieces solved. Good? Questions?
How do you find out
Relative and absolute? If it's the highest point possible. If my graph turns like this and never goes back up there again, that's absolutely my highest point.
So if it's one turn, then it's absolute.
Well, if your ends go into different directions like this, then it's not. Sometimes I have this. Sometimes, remember we made a W?
Yeah.
This would be your absolute minimum down here. This, therefore, is a relative minimum, relative max, because these guys are your max. If it's absolutely the lowest or absolutely the highest point, then you have an absolute one. Otherwise, you have relative to that area. Okay? Okay with this? Now, I'm going to do something else with this guy. Because, I have to just erase this. We also use synthetic division to find your roots. So this is a nice test question as well. Use synthetic division to find your roots. The first thing we had to do was locate one root. If I didn't give you an x equals, you had to go to your table and find me 1, 0. So look at your table and find me the x value, any one of them, when y is 0. 5? Okay, let's use 5. Now, we're going to synthetically divide this. So we pull out all your coefficients. 1, -4, is that a negative?
Yeah.
Okay. -5, but this is 3, 2, 1, and I need a 0 space holder. You've got to bring it all the way down. If your highest exponent is 3, 3, 2, 1, 0. So bring down the first one and start multiplying. 1 times 5 is 5. Add them down, 1. 1 times 5 is 5. Add it down, 0. And there's my other 0. Now, this guy is where my remainder is. I don't have one anymore. Okay, I need that last one to be 0 because that was a definite root. Because I divided this by an x, this is x squared, this is x. This is x to the 1, this is x to the 0. So your new function is x squared plus x. Now, is that factorable? Or do you want to synthetically divide again? We can factor that, and we can get your 1 and your 0 there. But you know what? Let's synthetically divide that again. Let's take this, or we can factor that. Let's take your 1, your 0, and divide it by another factor. What's another factor that you see in your table? -1. So I bring down my 1. 1 times -1 is -1. I get 0 times 0. There's my 0 that I had to get rid of. So this guy is where my x is. So y is equal to x. And so that guy would be where my 0 is. So I set this equal to 0, and I find my last one. And I found my last root. Your x-intercepts are the same as your roots. You can synthetically divide them, because sometimes, remember, we synthetically divide them, and then other times we can factor them. Everybody good with this problem? I thought this had a lot in it. A lot for you to remember. Yes? And so Aaron is remember your compositions. Always start at the right. So you're turning the f of x into the g of x. Write your f of x first, then your g of x. Take whatever was here and substitute it into that x. And you came out, we had to find the domain. So we came out with this function. And we said, second part of it, find the domain for that. One of your restrictions is under a radical, it cannot be negative. So we set it equal to greater than or equal to 0. I can't have a negative underneath there. And this was a nice one to have choices with, because if I didn't want you to stop at your equation only. I wanted you to remember to do the domain. So that kind of helps you say, well, there's my equation, it's not here. Oh, she asked me to do the domain. Sometimes you're going to get caught up in doing one part of it and you forget the other part. I'm going to go through them, but stop me if you have any questions. Here's another one of your oh, I always forget this, what they call them. Yeah. Okay, so here's another one. Just be careful, because you have to plug in that x plus h in both cases. Okay? Both of these. And an easy way to do it again is to make the x be over here. Map out your x and put x plus h in both of these. Your difference quotient. Now your goal, again, is to eliminate that denominator. That's a limit. As h approaches 0, if you go on to calculus, you'll use your difference quotient. And we're just setting it up for you in here, basically. So our goal is to eliminate that so that we don't have the problem of the 0 in the denominator. So be careful on this part, especially. When you subtract it, you're subtracting the entire function. So this has to have parentheses around it. This one, again, you have to do x plus h times x plus h. Can't take the shortcut. There's no shortcut with the binomial. When you gather your like terms, if something doesn't cross out, that only your h's can be remaining. If something else didn't cross out, then you know you made a mistake. It's probably distributing a negative sign. Okay, and we just leave it at this. And then you'll use that next year. Good? Okay, this next one, pay attention to this next one. This is a rational function. Rational functions we did a little bit differently. We have to get them to one side, and we have to get them under one denominator. If I had two terms, I have to move it to the other side and get it under one denominator. But this is under one denominator. It's one term. So we had zeros of the numerator, and we had zeros of the denominator. This is what gave you your cutoff on your number line. So once everything is to one side and in one term, then you take apart your zeros of your numerator and you do your zeros of your denominator. Now, if this greater than or equal to has an equal sign here, the numerator is the one that gets closed. The denominator will never be closed because the denominator cannot equal 0. So I found this root, and that's my denominator, so therefore it's open at the 1/3. I found this root, it's my numerator, it's closed. Now you're going to graph this function in your calculator. It doesn't fall like a regular parabola does. It has an asymptote, obviously, because that's where your asymptote is, as 1/3. So when you graph this, you'll see this. There's your asymptote. And if I wanted to know my limit as x approached 1/3, I would say the limit does not exist, right? The limit does not exist for this guy. In a minute, I'll do your horizontal asymptote or your limit to infinity, and we'll show you how that works. But for this part of it, you want to test where you're going with this. If your numbers are to the left of 1/3, let's use 0. 0 gives you a negative y. All you care about is it positive or negative. Between 1/3 and 2, use 1. 1 gives you a positive. After 2, look at after 2. The y is negative. Keep track of them in your sections. You wanted, in this case, the positive. So anything here is what you want, from here to here. Drop your endpoints. This one's closed. This one's open. Okay? Yes? By this. By the greater than or equal to 0.
Yeah, isn't that facing the 2? Isn't it facing the opposite of the 2? Or,
But your positive, you mean?
yeah, like, why wouldn't that, it would be,
I want,
is like, greater than or equal to 2?
no, not x. I want, where is your y value when x is over here? So if I pick like 3, where's my y value? It's in the negatives. The value of your equation is your y. So that's the guy you're looking at. Where is my y, positive and negative? Using these x values. It's almost like I take this little piece of this number line, see it? And I look at it right here. Anything to this side is negative. Anything to this side is negative. Only right in there is my little bit of positive. Okay? Now, you could also turn this into my horizontal asymptote. My degree in the numerator is the same as the degree in the denominator. So my horizontal asymptote says y is equal to negative 1/3. Yeah, look at that. There's my horizontal asymptote. If I look for my limit as x approaches infinity, I do the same exact rule and I just say it approaches negative 1/3. See how your limits tie into this? Your limits say, what are my end behaviors for this guy? Horizontally, my end behaviors, where my end's going, they're going to approach negative 1/3. As I come, x is negative, x is to the negative infinity to the positive infinity. My y asymptote is at negative 1/3. So my values, my end behaviors will approach that. So we kind of tie a limit into that as well. Okay. My limit as x approaches 1/3 does not exist. Causes me to jump. Okay with that? This one probably is a good one to remember because we did this a while back. All right, here's another comic in standard form. Right away, I know this is an ellipse or a circle because it's got an x squared and a y squared and a plus. But I notice that both of the coefficients are exactly the same. So therefore, it has to be a circle. If they're both plus and the coefficients are different, it'll be an ellipse. But your circle is a special ellipse. So when you get down here, you'll be able to see it. Do I have to divide by 7 to make that 1? No, because it is a circle. If these were different, then I would divide and make it equal to 1. Number 14, this was one of your interest ones. 8,000 is the positive, that's your principal. At a rate, make sure you move your decimal. Compounded quarterly for 20 years. T. You want to put it in your formula, and I'll give you that formula. And you round your money to 2 decimal places. It had to be rounded.
Isn't there like another formula?
Per?
Yeah. We're using that?
P. Well, that's continuously, when you compound continuously. Yeah.
Can you have that?
Yeah, I'll give it to you. I don't know if it's on there, I don't remember off the top of my head, but I'll give you that formula. Number 15 is a good one, guys. This is your reciprocal function. I want the domain of your reciprocal functions. So, or the range I should ask for. Easiest way is to start with your reciprocal. Secant, remember that your letters have to be different. So secant uses cosine. So I start like this. Here's my 90s, right? My cosine went here. Here's my cosine curve. My domain said all real numbers. My range said -1 to +1, right? Now, your secant goes off of those little hump things, if you will. But see where your asymptotes are your zeros. If this is a 0, and I say 0 over 1, when I take its reciprocal, I have 1 over 0. Can't divide by 0, right? So at your zeros, there's your asymptotes. Start like that. Your secant curve goes off of these little humps there. If I want to know what is the domain for this, I can use everything but where my asymptotes are. Just take a look at them first. This is 90, -90. What's this value over here? That's 180 in the middle. 270. So let's put these in radians. This is pi over 2. What's this guy? 3 pi over 2, because this is 1 pi over 2. 2 pi over 2, which is pi. 3 pi over 2. I notice on all the odd numbers, so n pi over 2, where n is an odd integer. I can use real, except when that happens to me. Remember doing this? Graph your original function, locate your zeros, because those you can't take the reciprocal of. Guys, let me just get through this sheet, because then tomorrow we have 3 to go over still. 4, 5, 6, 7. We actually have 4 to go over. Okay? Describe your transformations. Anything less than 0 gives you a shrink on this vertical. And whoops, oh, I did this again. Oh. Sorry about that. I realize I can't, for some reason, touch that. I'm not really concerned about 17.
That's not going to be on.
No. Oh. No. As long as you know your other ones. Shift to the right inside the parentheses. Okay, tomorrow, what I would make sure you do is go over